As you know, when the Fermat's last term was proved, there was a seminar going on in Cambridge, Newton's Institute, and 7 days continuous lecture by Andrew Wild, and at the very end he announced that therefore Fermat's last term had been solved. People were all amazed how that happened. But this man, he did not go to any conference, he did not go to any meeting. What he did, he wrote down 3 papers. First he wrote down the first paper, then he wrote down the second paper, then he wrote down the third paper, and he put all these 3 papers on archive.org. There is a website, all you know. If you have a result and if you think it is correct, you can put it there and then you see the comments of the people. It's not a journal. It's only that you get a priority if it turns out to be correct. He put this in 2003 and 2004, one by one, and it became very clear that these 3 papers, they really solved the point architecture. The whole world got into studying those 3 papers, and it was very difficult to immediately say that yes, the group is correct. It took 3 years for all the mathematicians in the world pursuing Poincare conjecture to go through those papers very critically and finally say yes, the solution is correct. And he solved the Poincare conjecture. And then in March in 2006, he was given the Fields Medal for this particular work, and as I said, it didn't come out of that. Now, this is the only problem out of 7 problems which have been solved. 7 Millennium Prize problems, this is the only problem which has been solved. The Riemann hypothesis is still a burning problem, and this problem again is not very difficult to state. If you know what is Riemann zeta function, Riemann zeta function is a function of complex variables, so you think of the plane and think of the line x is equal to half. And the claim is that all the zeros of this Riemann zeta function, they lie only on the line x is equal to half. This is the problem. And this is what Riemann made a hypothesis for, and it became known as Riemann hypothesis. It is still being pursued. Lots of solutions are being proposed, but the final solution is yet to be accepted, and it is in fact many people throughout the world, they are trying. So I have just only mentioned these problems because they will really advance the branches of mathematics, all branches of mathematical sciences. They don't lie in any particular branch of mathematics. They in fact, they cover the entire range of mathematics, from pure to applied or computer science and so on. All the mathematics will be necessary to tackle these problems. They have a lot of depth. And it's a very good thing that because these problems have been now, they are known as millennium problems. That means the time given to us to solve these problems is 1,000 years, from 2000 to 3000. Millennium Prize problems. And let us see how many problems will be solved and when they will be solved. So these are really very good. When you study these things, you go to the website and study these comments of the Fields medalists, how they have commented about these problems and what is their initial reaction, whether it is going to be true or it is not going to be true and so on. You really feel excited to do something. Of course, these are much beyond all of us, I know, but simply I have only expressed these here just to tell you that there is something which is lying still ahead of us, but that will be a noble cause if we can really do something about those particular problems. So with these few words, I would like to now wish this conference a grand success, and I am sure that a lot of good discussions will come out, and maybe some good problems are formulated or even solved. Thank you very much.
Thank you, sir, for your valuable insights on various mathematical problems. May I have your attention, please? Professor Ashok Sen, renowned physicist from Harishchandra Research Institute, Allahabad, has just arrived. We welcome you, sir. I again request Professor P. Singh to kindly introduce our director, sir.
Ladies and gentlemen, I have the privilege to have a brief discussion in introduction of Professor Chakravarti. Professor P. Chakravarti, Professor of Electronics Engineering and former Head of Department of Electronics Engineering, ITBHU, Varanasi, has taken over charge as Director of Motilal Nehru Institute of Technology, Allahabad, in last June 2011. Professor Chakravarti has made a significant contribution in experimental and theoretical research in the areas of microelectronics and photonics. He has been the coordinator during 2005-11 of the Center for Research in Microelectronics, Department of Electronics Engineering, ITBHU, and developed a dedicated photonics laboratory in the center. He was the former coordinator of the AMS Design Center at ITBHU. Following the tradition of Banaras Hindu University, Professor Chakravarti established interdisciplinary research linkage involving the School of Material Science and Technology, ITBHU, for developing flexible electronic devices, Department of Physics, Faculty of Science and Department of Microbiology, AMS BHU, for exploring the potential of graphene and other composite materials for developing sensors. During the past 1 decade, Professor Chakravarti developed a dedicated research team with his PhD scholars and graduate students working in various areas of microelectronics and nanoelectronics. He has also established strong collaborations with the Optoelectronic Research Group, Lancaster University, Lancaster, UK, and Nanomaterials Research Group, University of New South Wales, Australia. He has published 100 research papers in leading technical journals and 90 research papers in conference proceedings. He has delivered numerous invited talks at various national and international conferences in the country and abroad. He has authored 2 textbooks and edited 4 proceedings. Professor Chakravarti earned his BTech and MTech degrees from the University of Kolkata in 1980 and 1982, respectively. He earned his PhD degree in electronics engineering from the Institute of Technology, BHU, in 1988. He is a recipient of INSA Visiting Fellowship and Senior Visiting Fellowship of EPSRC UK. Professor Chakravarti is a senior member of IEEE and executive member of IEEE Indian AD chapter. So I now request Professor Chakravarti to address the
introduction, which was quite lengthy, was not needed probably. Anyway, our chief guest, Satyadar Tripathi, Professor HRI, then Professor Sivdat Kumar, Head of the Department, Professor Pritam Singh, Senior Professor, and Dr. Pritam Singh, distinguished speakers, delegates, dear students. I take this privilege to extend warm welcome to all of you to this conference on Advances in Mathematical Sciences being organized by the Department of Mathematics. I welcome you to this great seat of learning, MNNIT Allahabad. And this institute has been active in this kind of academic programs over the last 50 years. I'd like to share with you that the institute has completed its journey of 50 years of existence and has been mainly a center for technological studies. The scope of this conference, as our chief guest has said, is quite vast. Mathematics subject itself is a very vast subject. And this conference tries to explore these various advances in various areas of mathematical sciences. I congratulate the entire team of this, the organizers and the faculty members of Mathematics Department for coming forward and take up this challenge to organize this kind of conference. Since I joined this institute, my primary objective was to put emphasis on this kind of gathering, because this gives you an opportunity to interact with real experts and exponents in the area, and these people can boost you and guide you that what are the various areas where you can take up your career, those who are pursuing their career in the area of mathematics. I look at mathematics being an engineering student, particularly electronics engineering student. I feel that there is no existence of electronics without mathematics. And this is generally true for all engineering subjects. Why engineering subjects? Now, today biology also it is equally important to know mathematics, basics of mathematics. Otherwise your knowledge will not be complete. I was listening to that chief guest address. It was really excellent, and he was talking about this, how this kind of practices are there from 15th century, that announce an award and solve a problem. Today also the same thing, same tradition is continuing in mathematics. And he was discussing certain problems, simple problems which could not be solved. Simple problems could be as simple as squaring a circle and like that. And he was talking on drawing a hexagonal in a circle. You draw a circle with the same radius, you cut the arcs and draw an hexagon. And I was just thinking, wondering that whenever I used to try it, then the last arc used to cross that. So they are never meeting at the same point. This is a problem we used to face. Why is like this? After you get the 5 arcs, the last arc will be slightly crossing that. It's very difficult to get it. Why it is so? This is because mathematics is all idealized thing, right? We say point has existence but doesn't have any dimension. But when you try to draw, the point has existence as well as dimension, right? Because the compass, when you put, it punches and that point becomes bigger and bigger, and then last time falls short of these things. What I try to say this is that technology is something where it is in real practice when you do something. And mathematics, most of the times, they are idealized situations when you solve the problem. As engineers, we often find this kind of problem. When we simulate a certain system in engineering, mathematically, go to lab, design the system, we don't get the same result which we get from the mathematical modeling. In electronics engineering, we face occasionally this problem. One reason probably is that in any modeling, depending on the system you are modeling, you try to put them in terms of mathematical equation. Then the challenge comes that solving the mathematical equation. Right? In some practical problems, the mathematical equations may become so complicated that you do not know how to solve this equation. Right? In real cases, in fact, the equations, you get a differential equation to represent a system, and which is so nonlinear, you do not know a standard technique to solve the equation. What is the next step? Next step, we make a lot of simplifying assumptions so that the equation takes a form which we can solve. Right? Naturally, when it comes to designing the practical system, obviously because you have made lot of assumptions which are not really true under practical operating conditions. That's why your results are not matching with your mathematically solved results or simulation results. But here computer plays a big role. Computer has changed actually the techniques. I should not say the techniques were very much in place. But faster computation through iteration, computer has helped a lot, particularly for the engineering areas, technologies. It was a boom. Because you see that, I gave you an example that we simplified the equation so that we can solve the equation, get an explicit relationship, right? But computer has helped you in solving implicit equations through numerical techniques, be it algebraic equation, be it differential equations, right? And huge amount of computation you can do practically in no time. So we have taken help of the computers, and mathematics combinedly have helped the technologies to develop like anything. Now you see that the commercial softwares which are coming where thousands of engineers are working on practical problems, giving you a software in the form of a package, which most of the time is menu driven. Even you have to understand the problem, but still using it as a tool, you can solve many technological engineering problems, right? But there is a drawback of this. There is a tendency that people do not try to understand the problem and make use of these tools to solve their problem. This can be very, very dangerous because you do not know what is the basis of solving your problem. So today's engineer, my message will be to try to understand the problem, see the algorithm which is used for solving your problem, and you to the student strength. So number will be very good, and you are doing good research, and I appreciate that, and I take this opportunity here to congratulate all the faculty members for doing significant research, and there are a very good number of research scholars in the mathematics department, and compared to some engineering department, it's many more. And space, you was requesting head of the department to give more space to mathematics department. So I just said that for mathematics you don't require any space or any lab. Wherever you see a seat, mathematics can stack there. You need a piece of paper and your intellect. That is important for doing mathematics. But anyway, mathematics, I understand the importance of mathematics, and definitely I will try to strengthen this mathematics in the engineering, which is very, very needed. And my experience as an electronics engineer, I have seen that many of these electronics theory, even as simple as the frequency modulation when it was proposed, it was totally based on mathematics. And some of this electronic subject will look more like mathematics than an electronic subject. It's true. And most of the principles of communication today which have been implemented, they are all based on mathematics, starting from your Fourier series, Fourier transforms, and the latter form in the discrete form in first Fourier transform, discrete Fourier transforms. It's a whole mathematics, and the communication is full of mathematics. Likewise, in your semiconductor physics, quantum physics, this is all based on mathematics. So unless you understand mathematics, you cannot train yourself to be an engineer. So mathematics, so long as engineering, science and technology is there, mathematics will be there. So with these few words, I would like to congratulate the organizers again for organizing this conference.